Today in our video, we're looking at Newton's third law. We've seen Newton's first law and Newton's second law already, so now we want to talk about the first law a little bit, or third law a little bit more. And basically that's our title here, Newton's third law of motion. It's really an important law, and it helps us explain quite a few different phenomena or things that are happening around us. Again, that's Isaac Newton right here in the middle, and his apple which did not fall on his head. Okay, long story, we'll talk about that later on. But Newton's third law is also called the law of interactions. That's the term that we're going to use for it. You've probably also heard of it as being the law of action-reactions. That might ring a couple bells for you in terms of what we're talking about in this case. And you got an action-reaction if you're standing at a boat and you step off of the boat, what happens? The boat moves one way, you move another way, and you fall in the water. Unless you're stepping onto a dock. Or you might miss the dock because the boat might move faster than what you're moving. But it's all because of that action-reaction in terms of that interaction. Now we do have to be a little bit careful with that action-reaction term, but we'll see that in just a minute. So as we start off with, we have an object here. And if what happens in the law of interactions is if I put a force on an object, I do the red force, I've put a force on A. That object has put a exact same force back on me. So the force of A on B and the force of B on A, those are vectors that are the same length. They are equal. Not working. My pen isn't working. Oh, probably because I should go up here and hit my pen button. And it's still not going to work. Let's try that one more time. Pen, black. There we go. Those two forces are equal but opposite to each other. Now, how can that be? How can we have these two forces that are equal and opposite? And pretty much what it means is that what we have is we have an interaction pair. If I do something to something else, it's automatically doing the exact same thing back on me. And so you have two forces in opposite direction that have equal magnitude. Again, I put a force on something, it puts that same exact force onto me, no matter what that is. It always is there. So an interaction pair is also called that action-reaction pair. And so you can see in this case we have our two girls on figure skates. If the blue girl pulls the red girl, what happens? Since they're on figure skates, you have very little friction. They pull together. The force the blue girl puts on the red girl is exactly the same as the red girl is putting on the blue girl. Now the red girl isn't doing anything. She's not actually pulling on her rope. It's just that force the blue girl has put on is making the red girl move as well. They're both moving towards each other. And our little statement at the bottom here, whenever an object exerts a force on the second object exerts that same exact magnitude but opposite directions on the other object. Whether you have a hammer pounding a nail, so the hammer puts a force on the nail is putting that same force back on the hammer, or you're punching a wall, your fist is putting force on the wall, you have the exact same force putting back from the wall onto your hand. Even something falling. The earth is attracting it, right, because of gravity, but the object is also attracting the earth with that exact same force. Now, think about that. As you jump off a ladder, the earth is attracting you, but you're also attracting the earth. You're both moving. Interesting. We'll talk more about that in class in terms of how that motion is occurring. So here's a little joke yet for us. If you don't know who Prometheus is, you probably can look him up. It's from Greek mythology. But equal yet opposite reaction, it's kind of humorous. It's not super humorous. But you have Prometheus there chained into a rock. He got a god mad, and basically he was sentenced to be chained to a rock for eternity, and an eagle will come every day, eat out his liver, and it will grow back, and the next day continue the same thing. So the eagle laughs at him, he cries. It's equal opposite reaction. It's supposed to be kind of funny. We're all laughing very hard at this point in time, right? Or here's another one. Ninja powers activate. Ka-cha, kick the big rock. Oh. You moved, a ninja person here, moved a lot more than what the rock is. See, the rock just scooted a little bit. And I guess due to Newton's third law, every action does have that equal opposite reaction. But since the ball is putting that same force on me, and I'm much smaller than that great big ball or great big rock, I move farther than the rock did. That's kind of the same thing that's happened with Earth. There is an acceleration. We can actually use Newton's second law to calculate what that acceleration is. that the Earth would move with the force that we're exerting on it, we'll find out that it's very, very, very small, because Earth is much, 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 much more massive than we are. But still, there's equal forces being exerted there. Now, the one thing we kind of have to be a little bit careful of here is that this interaction forces are not a cause and effect. The force of one isn't causing the second force. Because I hit a wall does not mean the wall is hitting me back as I did that. Or we have our example here, we have a couple of skateboarders that are pushing in each other, and then as one pushes at the other, they move apart. Your push doesn't cause your friend to push back. When you put a force on something, there is always going to be that interaction pair, that other forces, opposite direction, opposite, same magnitude, every single time, no matter what. Those forces exist together, or they don't exist at all. You can't have just one force in any case. There always has to be two forces required. Forces can't exist singly. So here is a statement of Newton's third law, the one that you're probably used to. And for every action, there's an equal and opposite, or equal but opposite reaction. That seems like it's kind of cause and effect, though. If I do something, there's going to be a retaliation for it, for example. That's not quite the case, though. So we're going to change up our definition here that we're going to use for this a little bit. But, again, you can't have just one force. There always has to be the opposite force that works with it. So a much shorter definition, and hopefully that'll make a little bit more sense, is because we have forces that are interaction pairs, is that forces occur in pairs. You always have a force and its interaction pair force. And you can't have just one. There always must be two. Well, thinking about that for a second here, that takes us to our last slide here, which is going to be a question for you to think about that we'll spend a little bit of time talking about in class. And that question then is, if I pushed you, that means that the force I pushed you with, you are pushing back on me with at the exact same time, right? So if that's true, if those forces are equal and opposite, isn't that balanced forces? Equal size, opposite direction. Sounds balanced to me. How can we actually have motion happen then? Because doesn't Newton's first law say an object at rest stays at rest, an object in motion stays in constant state of motion unless some unbalanced force acts upon it? That's kind of an important question that's going to test us a little bit to try and determine what's going on. So think about that one, and we're going to talk about that in class and see what you come up with. See you tomorrow.